So let's consider some practice problems dealing with factorials. As in the previous one, I will display the problem, give you a few seconds to pause the video so you can solve the problem, then display the solution. If you're good with the solution, don't need an explanation, you can skip down to the next problem. I'll try to get links to the problem, to the time of the problem directly in the comments. If I can't get links up there, I'll start off with just listing the times and I'll figure that out later. If you need, you can sit through and watch a complete explanation of each problem. So for problem 1, or example 1, just 5 different factorial problems: 0 factorial, 8 factorial, 12 factorial over 9 factorial, 12 factorial over 9 factorial, 3 factorial, and n plus 1 factorial over n times n minus 2 factorial. Pause it now, solve the problems. Alright. Solutions are 1, 40,320, 1,320, 220, and n squared minus 1. So, relatively easily, we defined 0 factorial as 1, and if you're not sure why we defined it that way, go back to the previous video where I explain why n factorial, or 0 factorial equals 1. 8 factorial, well, I could just expand this out. 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1 and work it out. 8 times 7 is 56, dot, dot, dot. I could also, if this is a calculator problem, I could go to the calculator and just do 8 math, go over to PRB, it's the 4th one, factorial, 40,320. This one, now, I could do this in the calculator, but actually sometimes these problems in the calculator you wouldn't be able to get done in the older TI calculators. I don't know about the older Casio calculators, but you can do them by hand still. The problem is factorial grows very quickly, so you could see already 8 factorial is 40,000, above 40,000. Here's the trick. So we know that 12 factorial is 12 times 11 times 10. I'll show it all the way out. 12 times 11 times 10 times 9 times 8 times 7 times 6 times 5 times 4. And 9 factorial is 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. And we can see that here 12 is 3 more than 9. So we still have the 12, the 11, the 10, but everything else canceled out. And so all I need to do was 12 times 11 is 320. Or sorry, 132 times 10 is 1,320. So without a calculator, this is still an easy problem, still a quick problem. You don't need to do all of this mess because it's going to cancel out anyway. And figuring out how these cancel out is actually going to save you a lot of time and heartache for some of these problems. This works very similarly. So I could do the same thing. Let me list it all off, then I'll sort of explain what I like to do. So at the top we would have 12 times 11 times 10, all the way down to 1. In the denominator, you have to do these separately. 9 factorial times 3 factorial is definitely not 27 factorial. Some people think it might be when they first see factorials, but it's very clear. 9 factorial is 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. 3 factorial is 3 times 2 times 1. In nowhere are you getting 27 times 26 times 25. You're not getting nearly that large here. Now, I always sort of try to cancel out as much as possible when I do these. So I see that this sort of 9 factorial, the bigger factorial from the bottom, is going to cancel out the most terms from the top, so those will cancel out over division. And the next thing I usually do is this. This right here is going to give me 6, And before I even multiply this all the way out, I'm going to try to reduce things down. So this 12 on top and the 6 at the bottom is going to leave me with a 2 over 1. And so instead of even having to do 12 times 11 times 10, I just need to do 2 times 11 times 10, which is 220. Alright, final problem here, this one. So I have this n hanging out here. I'm just going to sort of have it here for now. But I notice that n plus 1 is 3 more than n minus 2. So there will be 3 additional terms at the top. I'm going to do the work down here so I have plenty of room. So I will have the 3 additional terms n plus 1 times n minus 1, and then times n minus 2 all the way down, so n minus 2 factorial. In the denominator, I have n and n minus 2 factorial, and we can see clearly that these cancel. We can also see that the n's cancel, and so I'm just left with n plus 1 times n minus 1. That's just going to be the difference of squares rule. N plus 1 times n minus 1. I'll FOIL it out or distribute it out or however the heck you want to say it. But it should be obvious we get here. So if I FOIL it, n times n is n squared, n times negative 1 is minus n, 1 times n is positive n, 1 times negative 1 is minus 1, n squared minus 1. Example 2. You have 5 textbooks that you want to arrange on a shelf. In how many orders can you arrange these books? Pause the video, take a little bit of time, solve the problem. And here we go. There are 120 ways. So there are 5 textbooks. You know that can be found by 5 factorial. 5 factorial is 120. And the more work you do with these, the quicker you just know 5 factorial is 120. 6 factorial is 720. 7 factorial is 5040. You just sort of start memorizing them up to a point, and these small problems are quick. If you didn't get this, you could have seen that we have 5 spots on the shelf to organize them. And for the first spot, we have 5 choices. Second spot, we have 4 remaining books. Third spot, we have 3 remaining books. Fourth spot, we have 2 remaining books. And the last spot, we only have 1 book, so there's really no choice once the other 4 books are chosen, and multiply through. Example 3. In how many ways can you rearrange the letters in the word product? Take a few minutes, pause the video, see if you can solve that. Alright, solution is 5040. We can see that there are 7 letters in this word. Each one of them is different. That's important. We'll get to that more in the next lesson or two. And so I could do 7 factorial, which is 7 times 6 times 5 times 4 times 3 times 2 times 1, which I guess I'll do it. But you get used to it. You get used to doing this faster. 7 times 6 gives me 42. Times 5 gives me 210. Times 4 gives me 840. Times 3, so 800 times 3 gives me 2,400. 40 times 3 gives me 120, so I get 2,520. Times 2 is 5,040. Times 1 doesn't change anything. And you could use the calculator if this is a calculator problem. It's not that tricky. Example 4. If you randomly arrange the letters in the word math, what is the probability that your rearrangement is a correct spelling of math? Pause the video, try to solve it. The probability is 1 out of 24. And the way we do this is we say, okay, if I rearrange it, well, there are 4 factorial equal to 24 ways to rearrange these. M-A-T-H, M-A-H-T, M-T-A-H, M-T-H-A, all the way to H-T-A-M. Only one of those ways is a successful spelling. There's only one correct way to spell math. So there are 24 possible arrangements. Only one of them is successful. So the probability is 1 out of 24. Okay, example 5. 8 people are running in the final of a 1,500 meter race. In how many ways can there be a first, second, and third place finisher? Take a few minutes and try to solve this. All right, there are 336 ways. So here's the idea for this. And this is going to lead into the next lesson. I'm looking at 3 places. Now, I'll put this next part in here. These are the ones I care about. The last 5 places don't matter for this problem. We don't care who gets 4th place. We're only looking at 1st, 2nd, and 3rd. And so in here, if I have 8 people and no one's finished yet, there are 8 possible first place finishers. Once a single person has finished, there are now 7. And once the first 2 have finished, there are 6. Now, it would continue 5, 4, 3, 2, 1 if I wanted to know how many ways there were to line up all 8 of them. But since I only am looking at the 1st, 2nd, and 3rd place, this stuff right here doesn't matter. So I'm just going to do 8 times 7 times 6, and that's going to end up giving me 336. Now before I move on, you might want to think, how could I use factorials to get 8 times 7 times 6? We already sort of saw it. We know that the way to arrange all of them was 8 factorial. But over here, we got rid of 5, 4, 3, 2, and 1. And that's 5 factorial. This idea, this concept, is going to lead into the next lesson. Final example, a little tricky problem. You are seating 6 people around a circular table. In how many ways can you seat these people when we consider a rotation of a seating assignment to be an identical seating assignment? Pause the video, take a few minutes to solve this. Okay, so there are 120 ways. And here's what's going on. We saw a lot of things where we lined up 6 things. Now if we were just lining up these 6 people, then there would be 6 factorial, which is equal to 720 ways. But we're not lining these people up. Instead, we're putting them around a circular table. 1 here, 1 here, 1 here, 1 here, 1 here, 1 here. And if this table had direction, if there was some sort of order to the chairs where this chair is different than this chair, then there would still be, 6 times 5 times 4 times 3 times 2 times 1 ways to arrange these. But here's the kicker. We say that a rotation is identical. So if I assign the seating A, B, C, D, E, F, with A at the top, or I assign it B, C, D, E, F, A, with B on the top, these are considered identical seating. And as we can see, A could be at any one of these 6 spots. So there are a couple of ways to consider this problem. One way is to say, okay, if I line them all up around here, I get 720 ways to seat them, but each one of those 720 ways is repeated 6 times, because I could have A up here, or A 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 here. So I'll end up dividing that by 6 and get 120. The other option is this. The other way to look at it is this. I have a circular table. All the seats are the same. The rotations are considered identical. So if rotations are considered identical, then I'm just going to say, all right, let's force A to be this top seat, so it can't be anywhere else. And now I just have 5 seats remaining. So 5 times 4 times 3 times 2 times 1 is also 120. Now this problem with rotations gives me 120. Just so that we know, I could also have done this with just considering that the person you're sitting next to, and then we not only get rotations, we also get reflections, and there are only 60 ways to do that, because each one of these has a reflection that would be identical. But this one, we're just talking about rotations. We're considering that someone looking to his or her right and looking to his or her left will notice the difference if those people are switched. All right, I'll continue on with more of this next couple of days. Leave a comment if you have questions about this or requests for other videos.